Thanks to the organizers for inviting me to give this speech. In recent times, I did a lot of work on tunnels, and I could really appreciate all the pros that this software has in comparison to others. I will try to make some considerations about this during my presentation. First of all, I would like to give you a little bit of introduction on the topic. Now, this slide is titled that it points out that Italy is a difficult country from many points of view, but I will now focus on topography because here, if you see the map where we have our lovely boot, you can appreciate the fact that the zones that are in green are very small. So we are 60 million people, but if you look close into the map, you realize that there are not so many areas which can be populated, and most of Italy is mountains. You can see the Alps, which of course allow us to have some generally nice weather because it protects us from what's coming from Northern Europe. Then we have the Apennines, which run all along the peninsula down to the south. And then there is this valley here where Milano is, which is practically the only flat area which we have, the only extended flat area we have. There are other portions. And this is just to mention that every time you have to think about infrastructures in Italy, you have to take into account the fact that you have to build tunnels. As a matter of fact, if you look into the figures, you realize that Italy has approximately 458 tunnels open to traffic. We're speaking about road tunnels, which is something like slightly less than half of the European total of this trans-European road network. So it's a lot of tunnels. Actually, in this area here, I heard a statistic once that in this small area, which goes to France, we have a number of tunnels which equals the number of tunnels in whole Spain. Just to give you an idea. So tunnels is a big topic for us. As a matter of fact, if you look at some notable projects in the last years, you realize that there's been a lot of work going on in this topic. So we have a new line from Napoli to Bari, which means basically from Naples to the other side of the peninsula, where facing Albania and Greece. Then we have some new galleries in Sicily on the main direction from Palermo to Catania. Other galleries, I would like to mention this gallery here, of which you see the data here, which goes from Milano to Genova. This is a strategic infrastructure, of course, because Milano doesn't have the sea. Genova is one of the largest ports in Italy, so you can appreciate the importance. There is also one side effect. This allows the people from Milan to go to Genova. The people from Genova don't like the people from Milano, but they have to handle this. The statistics here are in Italian, but you can appreciate the importance of this gallery, this Valico gallery. So we have 53 kilometers overall, 70% of which are in gallery. The speed of the train will reach something around 250 kilometers per hour. It's not the maximum of the high-speed trains in Italy, but still a lot, and it makes Milano-Genova less than 1 hour in terms of time. Here are other data, but I will move on. It's not just Italy, we also have our beloved neighbors from Switzerland. And this slide I took just to show you what's been going on in Switzerland as concerns the Gotthard Pass. They are building a huge underpass over there. And this allows me to show you a little bit of what the typical deep tunnel section is, because today I'm talking on deep tunnels. And this goes well with the presentation by Thomas previously, because he spoke about shallow tunnels, so we complement each other. Just to mention that differently from some of the structures we saw before, deep tunnels have a simple geometry. Basically, you have the lining, which is usually, if it's a deep tunnel, it should be a circle. Of course, there are other possible shapes, but the most of the optimized shape is typically the circle because of the surrounding pressure, which could be, as a first approximation, considered as a uniform pressure. And then there are typically some inner portions with vertical and horizontal partitions, which also could require some study. So just to break down the problem into simple things, I would mention that in fire-related problems that involve deep tunnels, we are typically faced with two types of problems. You have horizontal and vertical partitions where you could face a local problem, which of course is not less important because it implies disruption of the traffic and therefore huge economic losses, not to mention the possibility of having human losses. But this problem I will not focus on because mainly from our experience, it can be tackled the way Thomas did with shallow tunnels. If I was to simplify it to the most, I would say we're talking about beam-like elements and column-like elements. What I'm going to talk today about is the lining problem, because on this type of problem, we did some work during the past years and we also compared different approaches. We are now working in a FIB group on a bulletin which should outline what the best way is to approach the problem. So I will show what has been done concerning SAFIR in terms of modeling and also in terms of main results, which are interesting to outline a little bit how the problem looks. And inside this problem, in my opinion, and from what I saw during the last years, there is one main problem. One main problem which may appear simple, but which has to be tackled in a correct way if one wants to do things properly. And the main problem in modeling deep tunnels is the soil structure interaction. Now, what happens typically is that the design is governed by ambient temperature conditions. And more specifically, with this respect, a key role is played by the load exerted by the soil on the lining. So what typically happens is that there is a geotechnical analysis with softwares. I put here two names I'm aware of. Plaxis and FLAC are probably the ones which are more often used in Italy. And then the results of this analysis are provided to the fire engineer, to the fire expert, as a sort of initial condition to be used in the structural fire analysis. So what you receive is the geometry of the lining, and you receive a distribution of normal stresses sigma and tangential stresses tau on the outer surface of the lining. Now one has to handle this load very carefully, otherwise you will lose part of the problem. My first considerations on this is that the boundary stresses as they are provided are the result of a structural analysis which includes the lining. And this means that if you use them again as a boundary condition on the lining, this will in a certain sense result in counting them twice and in a lower value of the internal forces. Regardless, on this I'm focusing later on, whether the initial condition is relevant or not. So you have to be aware of this. In a certain sense, to put it in other words, these boundary stresses are the result of an equilibrium process, which includes the lining. So you shouldn't use them as such. There should be a pre-processing on these stresses. And then, of course, how can the soil be properly incorporated into a model? How can it be modeled in such a way that this condition is respected and its interaction with the lining upon fire is correctly captured? For the first problem, I already spoke my mind. You should always use as boundary stresses those immediately prior to lining insertion. This is usually not a problem because the geotechnical analysis is performed in different steps, so you may ask the geotechnical people to provide some stresses before the lining is inserted. And then the boundary stresses cannot apply to the lining alone as external loads, because this would imply constant loads, and this is typically something which does not take place in fire, especially if we have statically indeterminate structures where there is an evolution of the internal stresses. So you should do something else to capture this to capture the soil behavior, soil is usually modeled as normal, no tension springs. But then how do you apply the loads contemporary to springs at the boundary? Now, coming to the spring element in SAFIR, this is what we have in the manual. This is the definition of the spring. What is mostly interesting is the constitutive behavior of the spring model in SAFIR. Because as you see, it is an elastic, perfectly plastic constitutive model, which allows, upon proper definition of the upper limit, the lower limit, and the offset between the two, to define a certain preload in the spring. So you could add something which is like a load which is in the spring when the spring is in the zero position. And this, in my opinion, is the key to the problem. Here is the model, the typical model of a deep tunnel. This is the geometry. So you see, we make the geometry with beam elements. This is the circle. And then you have the springs all around, typically at a certain distance from each other. This can be taken into account in SAFIR by defining the area and the constant and properly transforming something that is like a subgrade into concentrated springs. So two possible solutions that I've seen done in the past is soil is modeled as a spring, the lining is modeled as beam elements. The pressure P0, which is the boundary stress, the initial condition which I mentioned before, is applied as an external load to the system which is formed by the lining and the springs. Now, if you assume an elastic behavior and you go through some simple equation, you realize that this results in the pressure being shared proportionally to the stiffness of the two components. And this leads to a problem because if your springs are not tension, to model the fact that the soil is not able to carry tension, the soil will be subjected to tension, and this will lead to numerical issues because basically the lining will have no boundary restraint. So it will result in something being able to move around, okay? On the contrary, if you use the same modeling strategy, but you use the pressure as an applied preload to the springs, by doing the same passages I mentioned before, you end up with the same pressure in the lining, and in the soil represented by springs, the pressure is rather a decrease of pressure. So the springs will remain in compression and you will not have any numerical problems. I should also mention, this was clarified by Professor Franzen during his presentation at the last Crossfire event, that there are other strategies to overcome the problem with springs all around the circular lining, all pointed towards the center, which means they are not able to accommodate torsion. There are other strategies, if I remember well. One strategy to overcome this problem is, for example, to go into dynamic analysis, and this allows you to get a solution. Anyway, the key point of this slide is if your attention is on the lining, both approaches can work. You have to take into account that if your springs are no tension springs, you may have numerical issues. So, in my opinion, preloading the springs is something which is preferable. It also makes more sense from the mechanics point of view. As a matter of fact, the soil acts like a preloaded spring. And these equations, for those of you familiar with it, resemble very much what you get when you evaluate the elastic loss of pre-stress at the beginning of a pre-stressing procedure. It's exactly the same. It's two elastic entities which interact, one of which is pre-stressed, the other is not. And you get more or less the same equations. So going further, this is what it will look like in the SAFIR input file. So you have the definition of the springs. Here you see the angles which range from 180 to 107 minus 170. It's of course the worst case when you have to model all the lining, because geotechnical people are very accurate and very precise, so they hardly ever have a perfectly symmetric distribution of stresses. There is always something that goes into the way, so you have to model everything all the whole lining. If you model only half of the lining, it would be much easier also from the point of view of numerical stability. You could take into account symmetry with perfect restraints, and this would simplify things by a great amount. Here, I would focus on the last column. This is where you could define the pre-stress. Of course, it's entered in Newton. I think I got the units of measure right. The other are limit values, one in compression, the other in tension, the elastic stiffness, and I think this is the area of influence of the springs, if I remember well. So, and this is how this aspect could be implemented into SAFIR. So now a little bit on the model and how we used all this. We did some expertise work. I cannot show that. I will show what we are working on, and it's a paper which will be published, I think, in the near future. We compared, as I said, different modeling strategies. One is SAFIR, the other is Abacus, so another type of finite element software, and another is a simplified approach we've been using a lot in the last years in Milano. So here is a reference model we built with the following data. Nothing specific to mention other than the fact that materials are basic materials with 30 megapascals and 500 megapascals strength. We use the new mixed curve, which is provided in the new Eurocode, so a curve which is not two bounds. It goes from what was the upper bound, then it goes to the lower bound, and then we consider possible different stresses applied on the lining, one in the vertical direction, the other in the horizontal direction, because the fact that you have a uniform pressure is hardly ever the case in real applications. And as a reference, the ISO 834 fire, because to understand the phenomenon and to see how things evolve, the ISO 834 fire is as good as other fires. Here are parametric analysis we carried out looking at the geometry, so thickness and radius effect, the materials properties, concrete strength and conductivity, and then the fire scenario and the exposure, which is of course interesting when you have the type of geometry I shown before. Some results. This is, for example, the role of the radius. What I would like to mention here is that okay, we have to be precise on modeling the initial condition, but then when fire takes place, as you see, there is such a big increase of the actual force that it offsets in a certain sense the initial condition. Here, the actual force is plotted inside the lining, but you have to think about the fact that this actual force is directly linked to the pressure exerted on the ground from simple equilibrium considerations. On the contrary, the bending moment does not vary that much if you change the radius from 6 to 3. And this is because the bending moment is rather an axisymmetric effect. So the lining is a circle because of symmetry. It cannot become something else than a circle. So this is rather a perfect restraint moment, which mainly depends on the properties of the section rather than the overall geometry. Then this is the role of concrete strength. Here there is a visible effect also on the moment because, as I mentioned, if it's section related, if it's section based, then of course increasing the strength leads to a higher bending moment. So this is expected. Changing the strength from 30 to 50, you see an increase. Apologies. This, of course, people are always curious about changing the fire scenario. And what we see here is that the fire scenario does not play a big role, nor does play a big role the fact that you expose the whole inner surface or you consider that the bottom is unexposed because of the geometry as shown before. So there is typically an area where the fire cannot reach. You can see that if you focus on either the actual force or the bending moment, the results look pretty much the same. As a matter of fact, the bottom unexposed, so with areas of cold concrete, this could even result in a worse situation because of the restraint offered. One thing which is interesting and which is much simpler in a beam-based elements like in a beam-based element like the one I showed, rather than in a model which you could develop with a software like Abacus is the inclusion of joints, because joints in a beam-based element can be included as hinges, which are very convenient. You use the beam release function, I think it's called in SAFIR. Again, not a big difference in terms of actual force if you consider no joints, two joints, or three joints, but a very significant difference in terms of the form shape, because you can see here in the case of two joints, and here you can see in the case of three joints, there are big rotations which take place at the location of the joints. So this has to be taken into account, because these locations may be required to have some additional checks in terms of rotation capability. If not, if none other things take place, simply because of the detailing, there can be portions of the joints which are not allowed to rotate with respect to each other. Still, if you look again at the bending moment distribution, you will see that the maximum values of bending moment are not that much affected. They simply have the 0 points where the joints are located. And this is basically the output that comes from SAFIR, shown on half of the lining. So you can see here the case of two joints. I put here four because this is of course half of the model, and here the case of three joints. What we are usually asked when we do this type of analysis is, so did the model reach collapse? And we say, no, the analysis ran to the end, which means the tunnel did not collapse. And then people are suspicious because they say, so you judge on collapse or not simply on the basis of the output of the software? We want to see the comparison in terms of M envelopes. Okay, so this is the comparison, for example, of the output from SAFIR, which are the dots here in different colors, which independent calculations we did with another homemade software. And you can see that these points are always inside the respective interaction envelope. So you have to compare the blue with the blue, the pink with the pink, the purple with the purple. And this also explains why all the curves I shown previously, at a certain point, they flatten down, because basically the system tends to attain its ultimate or plastic limit capacity. Same takes place in the case of no spalling or with spalling with SFRC sections. So not that big differences. Of course, the colors are decisive, because otherwise you would judge that these points are outside of the respective interaction envelopes. Just to mention one thing that was mentioned before, looking at the stresses, again, there are people who are suspicious even in the case of interaction envelopes, and then they ask you, okay, but show me section-wise what happens in terms of stresses. No problem. You plot the stresses from SAFIR, and here it's a profile, but basically what I did is I put all the fibers in a 2D section, because they look like a profile simply because the centroids do not coincide. So what you're looking at here looks like a profile. As a reality, it's the plot of all the fibers, because they all have different centroids. And you compare it in this case with the profile which represents the strength at two different fire durations, and you see that all the stresses are below. So three types of the same verification: the analysis which runs to the end, the interaction envelope, section-based, and then the stress verification point-based. So everyone is happy when sees that. I remember one discussion I had many years ago with Professor Franzen, when I gave to him the question which was posed to me, and he simply replied to me, when you do nonlinear analysis, the checks are implicitly included in the nonlinear analysis. This is a concept which is very simple. It's sometimes hard to get it to the people asking for the analysis. Conclusions I made during my presentation, so I will not take more time, and I thank you for your attention.